So yeah, it started. So in last class, we talk about different attribute types, right? If you remember very clearly. So we talk about categorical attributes and ordinal attributes, and then the numeric attribute and so on. Okay. So what we do it for any data mining application, basically what we need to do it, we need to compare one object with another object. Okay. So then naturally we need to find that how the two objects are similar, or maybe the other way around, that two objects are dissimilar. Okay. And then, as I said that earlier, here objects means we should have set of attributes which basically describe the objects, and we have that attributes, and then only using those attributes we need to decide whether two objects are similar or not. Okay. So therefore, in today's topics, basically we'll talk about similarity and dissimilarity measures. Okay. So there are two things. One is similarity, another is dissimilarity measures. Similarity measures basically indicates that I think, is it not in the full screen mode? Yeah, now is. I think now it is in full screen mode, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So numerical measures, basically similarity indicates the numerical measures how the two objects are alike. So whenever the value is higher, it indicates the two objects are very much similar to each other, and highest value will be 1 whenever the two objects are the same object. Okay. So on the other hand, that is the dissimilarity measure is the opposite of the similarity measure, as the name suggests that dissimilarity measures is like a numerical measure. It indicates how far the two, how different the two objects are. Okay. So lower, whenever the lower the value, then objects are more alike, and it is reverse for the others. Okay. So now one example of the dissimilarity measure is the distance measures, right? Whenever the distance between two objects, okay, if very less, then what do we say? We say that two objects are quite similar to each other. So therefore, this has the name that is it is a dissimilarity measure. So when the value is less, two objects are more similar. Okay. So therefore, distance measure is one example of dissimilarity measures. And then one popular term is used in this case is called the proximity measures. So proximity measure basically refers to the similarity as well as dissimilarity. Okay. So whenever we talk about the proximity, it is basically both the things we are talking about, or both the things means either we are talking about similarity or dissimilarity measures. Okay. So now we'll see in the next slide how basically we compare the similarity or dissimilarity measure. How do you compute? Not compare. Compare is also okay, but we basically want to compute. Okay. Compare, as I said, whether two objects are same or not. But compute is more details. It will give some numerical value. Okay. Therefore, we can compute. Here we'll go in the next slide. Yeah. So as we learned that we have to describe an object, so we should have a set of attributes. Okay. And then we learned that basically we have four types of attributes. One is nominal, ordinal, and then numeric one. And numeric one has the category that is interval and ratio. Okay. So in case of the nominal attribute, I already said earlier we can say only whether two objects are same or not. An example we said so let's say we have two colors, okay, red and blue. If the two objects have color red and blue, we can say that two objects are not the similar as far as the color concerned. Okay. So therefore, what we can say is if so let's say X is the red and Y is the blue, if it is same, then we'll say is 1. Okay, this is a dissimilarity measure. So we should go here, right? So if the both objects are same, that is color is same, then only we'll say is the object are same. So that value will give you the similarity value will be 1. Okay. And if it is not, then it will be 0. We cannot do more than that. I told earlier example, if we add means addition, we perform the addition between red and blue, we don't know what will happen, and we don't know actually what is the results. So we can only say if the two objects are same, means as far as the color concerned, that attributes value will give 1, otherwise 0. As I said just few minutes before, that is the dissimilarity measure is the opposite of a similarity measure. Okay, so therefore, whenever this is 1, it should be 0. Whenever this is 0, and this should be 1. Okay, it is so simple. Next is ordinal attributes. As I said, the ordinal attribute basically gives the order of the objects, you can say, or order of the values. Okay, so as I said, the say large, then medium, and then small. So it gives an order, or you can say the rank of the students, or you can say grade of the students, and so on. So as I said earlier, that ordinal attribute also we cannot perform that addition. It does not make any sense whenever you add rank 2 and 3. Okay, it does not give any information. But what we can do it little better than earlier, we can find the what is called the similarity measures. How do we find the similarity measures? We will count how many distinct values are there. At example, say large, medium, and small. So we have 3 values. Okay, so now we want to find the distance between large and the small. So there is only one value. So what we should compute the value, that is 1 minus d. And what is that? D is the distinct number of values here. Okay, that is the difference here. So distance on the other side, that is distance d equal to x minus y, whatever the values are large and what did I say? Key small divided by n minus 1. What is n? That is n is the number of values. Okay, so that gives the ordinal value, and then whatever you find the value of d, and similarity is opposite of the dissimilarity measure. So in this example, what we do it, we'll find the dissimilarity values first, and then what we'll do it, as you know, the similarity basically confined between 0 and 1. So therefore, what we do it is equal to 1 minus d. And then say, let's say two objects is having the attribute value, both is having attribute value is, let's say, large. Then what will be the value? So x minus y itself, it will be 0. So therefore, this will be the maximum value. So basically what we are doing here, the values is mapped to the integer 0 to n minus 1. 0, so let's say we have 3 values, that is the large, medium, and small. So we map these 3 values to integer value, that is 0 to 1. So large is 0, then medium, and then small. So we'll have 0, 1, 2, and then we can compute the values of dissimilarity and similarity. And then is the numeric. Numeric, actually we have more choices. Say like we can compute the whether the two objects are similar. Have the hello.
Yes, sir.
Is there any issue?
Sir, you are not audible clearly.
Hello, now?
Yes, sir. You're
Yes, sir.
audible
It is audible now.
Just I think a few seconds it was problem. Okay. So I am actually outside in the institute.
Sir, can you please explain that ordinal attribute once again?
Yes, sure. So in ordinal attribute, ordinal attribute, what I'll do it, say ordinal attribute, we have that large, medium, and small. So you have 3 distinct values. We map these values to corresponding integer values or positive integer values starting from 0 to n minus 1, or say natural number 0 to that particular values. What is that particular value? So small we can indicate 0, then medium we can indicate 1, and large we can indicate 2. So therefore the values are mapped to integer 0 to n minus 1, and where n is the number of values, that is we have 3 different values. So we are mapping from 0 to 2. Now we have to compute the distance between dissimilarity measure between, let's say, for large and small. So large is 2 and small is 0. So then you will have 2. 2 divided by n minus 1. Okay. So n minus 1 is 2 minus 0, right? 2 divided by n minus 1. What is the value of n minus 1? That is 2.
2.
So the what value will get it? So you will get the 1. So dissimilarity value is 1. Okay. So then what is the similarity value? Similarity value will be 1 minus 1. So it will be 0. So there is no similarity between that large and then small. But if you compute between large and medium, then what will value? This will give you 1 and this will give you 2. So that is half. Okay. And then 1 minus half, this will give also similarity will be also 0.5 and dissimilarity value also will be 0.5. Okay. So now in case of the interval or ratio, you take the absolute differences. So that is commonly we say this is L1 distance, that I will see in the next slide, subsequent slides. And then as I said, the similarity is opposite to dissimilarity. So therefore what we can do it, we can simply take the whatever the value is there, we can take the negative. But here problem is, as I said, the value ranges between 0 to 1. So therefore you can not take in general. I said in general the value ranges between 0 to 1. So this we cannot take. So what we can do it, we can do this one, s equal to 1 by 1 plus d. Okay. So it is in a sense it is the inverse. Otherwise what you can do it, e to the power minus d. Okay. Or there may be another formulation for computing the similarity. Okay. So do you have any question here at this point?
No, sir.
No,
Sir,
sir.
in interval or ratio, which one of these we use to calculate the similarity?
For both the cases. Oh,
No,
achha,
sir.
you are saying ki in case of similarity.
Yes, sir.
See, it depends on the specific applications. Problem with this application, as I stated earlier, key similarity should be within the range 0 to 1. But if you see here, this is coming negative because this should be the positive always, and therefore this will be always negative. So you cannot take this one. But some application, if it is permitted, then obviously you can go with. Okay.
Okay.
Now, in other case, what you can do, you can safely you can take this part, s equal to 1 by 1 plus d. Even you can take 1 by d, but problem is d, if it is 0, then it will be an unstable case. So therefore it is written s equal to 1 plus d. Achha. Now if you want to take that we are expecting the similarity is nonlinear, then obviously you can put s equal to e to the power minus d. So there is no problem of having negative here. Okay. So on many application, people take this part. Otherwise, simple way you can take 1 by 1 upon of the what is called is distance or dissimilarity measure, or other way is this one. This is also a normalized one. Okay. Now it depends on the
Okay, sir.
applications.
Okay, sir.
So now we talk about Euclidean distance. You know that how to compute the Euclidean distance. That is way only you just note it one thing. If this is like dimension. So we generally compute the Euclidean distance between say between two-dimensional points on two-dimensional or three-dimensional. But we can have the multi-dimensional points. But on Euclidean space, then we can compute the distance here. Okay. But as you know that distance for, let's say, if for any points, distance can be computed using kilometers, using centimeters, using millimeters. Okay. Now these value will change, right? So if you compute the same Kolkata to Bhubaneswar distance in kilometers, that will be different. And if you compute in light years, okay, or if you compute in millimeters, okay. So therefore, problem with Euclidean distance is we need to have, say, standardization is necessary, and because it scales difference. Okay, it is not only, this is for maybe one attribute. So you are comparing, say, what is the beauty of the two cities. Okay, so or comparing two cities, then first what we can do, what is the characteristic, what is the radius of the corresponding city and population and so on. So population is one thing. So you are representing population in crores or million. Whenever you can computing in a small city. So let's say in Rourkela. So we compute Rourkela with compare with Rourkela with Mumbai. Okay. So now if you see that Rourkela's radius, if you compute, so let's say we compute for to show it much bigger, we can compute in a meter. But if you do the same thing with, say, Mumbai, so that will represent, but meaning is same, it will represent a different thing. So therefore, Euclidean distance is having a problem in scaling. So you need to do the scaling before applying the Euclidean distance many of the times, not if it is not all, because if the all values is ranged between, say, all attribute values ranges almost 0 to 10, or let's say all values ranges from within a specified range, then obviously there is no need for scaling. Otherwise, people generally go for the scaling. Okay. So yeah, this is one example of Euclidean distance. That is okay. I think I can skip simply. So this point I should mention here. So what we do it in case of the Euclidean distance, we take the square. Okay, here attributes difference, we take the square, and then we take the summit, and then we take the square root. That is for Euclidean distance. Now there is something called the Minkowski's distance. So that is the generalization of the Euclidean distance. Okay. So you know the meaning of the generalization, right? So you'll get the Euclidean distance, but it is more generalized form. How it happens? Say, let's say if you take r equal to 2, that means attributes difference square, and then this is nothing but the square root. So that reduced to Euclidean distance. Okay. But if you put any value of r instead of square in the earlier equation, here instead of square, if I put 1 or 3 or 4, whenever we change it here, so instead of square root, we'll take the square of other values also. Okay, 1 by 2, 1 by 3, 1 by 4, and so on. So let's say here, so what do you do it? Yeah, so if r equal to 1, okay, so then we only take the absolute differences, and then here 1. So you just add it, and then you will get the distance. So that is something called L1 distance. If you take square, that is something called Euclidean distance. And if you take 3, so this also you have to take the 1 by 3 power. Okay, so it does not have any name, but it is like a part of the Minkowski's distance whenever the value of r equal to 3. So here is where r is a parameter, n is the number of dimension. So here the sum is over number of dimension. Whenever you take it, so it is a different. So don't confuse with n or r. So that is why they're saying is please don't confuse with n or r. N is like a number of dimension or number of attributes, number of features. Okay. Whereas this is like Euclidean distance square. For here is it is 1 and so on. So r can have the value 1, 2. Obviously it is a what is called is integer number, positive integer. So starting from r equal to 1, 2, 3, 4, and 5, and so on. Okay. So now we'll see r equal to 1. It has a name, that is the city block distance or Manhattan distance or L1 norm. Okay. And r equal to 2, it has a name, that is Euclidean distance. So r equal to infinity, that is something called L infinity norm or L max norm, and so on. And here it's very specifically said, do not confuse r with n, where r is that norm and n is the number of dimension. Okay. Now one example here. So there is no need to show in details, but I will very carefully you just see it. Generally, I used to at least give 1 marks question from here, how to compute the L infinity norm. Okay. So here, so let's say point P1 on 2D. I want to compute the distance between P1 and P5. Okay, as you can see. So what will be the L1 distance? P1 and P5. What is the formula? Formula says you take the absolute difference of the each attributes. So absolute difference of each attribute x 0, 5. So absolute difference will be 5. And then you take the absolute difference of other attribute 2, 1. So this is 1. So now you take the summation of these two values. So it will be 6. So ideally P1 and P4, you should have the value P1 and P4 should be 6 for L1 distance. Okay. I think you can follow me, right?
Yes, sir.
Yes, sir. Yes, sir.
Very good. So now there is nothing to tell about the Euclidean distance. So now we go for P1 and P4 for L infinity norm. So L infinity norm is something like that. Key formula, if you see here. So this should be infinity and 1 by infinity. Infinity means what? So wherever the difference is maximum, so that will take the lead. Okay. So therefore, that it is defined here is like this is the maximum difference between any component of the vectors. So for any dimension, if you see the maximum of the all others, so that value will be the L infinity. So now let us consider for P1 and P4. So what is the difference here? Absolute difference is 5. Here absolute difference is 1. So higher is 5. So therefore L infinity norm will be 5. So you compute P1 and P4 is 5. Okay. So I take one more example here. Let's say we compute P2, P3. Okay. So here is difference is 1. Here difference is 1. So therefore P2, P3 will be 1. P2, P3 will be 1. Okay. So you can take some other example. Let's say here P3, P4. This is difference is 2. This is 0. So P3, P4, P3, P4 is 2. Okay. So this is something called L infinity norm. Okay. So there is one related distance computation is something called Mahalanobis distance. I don't know whether you have heard the name of the Mahalanobis or not. So PC Mahalanobis is Indian and he is the founder of Indian Statistical Institute, Kolkata. Okay. So he founded this institute long back in 1932. He's very famous statistician. Okay, you can say he is the only means he was the first and only recognized statistician in India, and that during that era, and then he only maybe he spread the knowledge that statistics, apart from physics, chemistry, and other science, statistics also play a major role. Will be playing a major role in deciding the other societal what is called is upliftment things or other thing, or maybe it will take a important role in economy and so on. So he established this institute. So this distance is something called the Mahalanobis distance. This distance has a different beauty apart from the Euclidean distance. Euclidean distance is long before it was invented, as you know. So whenever we compute the distance between 2 points, in case of the Euclidean distance, only we consider the 2 points here. We don't consider the in-between points if there are any points. But Mahalanobis distance, whenever it computes distance between these 2 points, it also takes care of this set of points, like distribution of these points are taken care. So therefore, in Mahalanobis distance, there is a term is called the covariance matrix. So in order to compute distance between 2 points in case of the Mahalanobis distance, so we have to consider the distribution of the points. Okay, so if we say the height of men in India will be different if you go to the height of 2 persons, not men, 2 person in, let's say, if you go to the Poland. Okay, so therefore, if you only compute the any two, say, let's say 1 person you have taken from Poland, another person from India, and then if you compute the distance or dissimilarity, so that will be totally different if you compute the 2 person in India and or maybe between 2 person in Poland. So what I wanted to convey with this one is like, so what are the other points in the data? What is their role also considered while computing distance in case of the Mahalanobis, and therefore this distance measure is so popular because the other points have also the values and those are considered. Other points, how it is considered is like it first compute the covariance of the entire data set and that is incorporated into this equation here. Okay. So this stand for the what is called transport, and this is transport of the matrix, transpose of the matrix, and this is like covariance, inverse of the covariance matrix. Okay. So one example here, 2 reference points is having the Euclidean distance 14.7, but Mahalanobis distance is 6. Okay. So now how to compute the Mahalanobis distance in the next slide, very quickly I'll tell. So here we go. Yeah. So covariance matrix is once it's computed, we got the covariance matrix here. Now we have a point A to B. Let's say we want to compute the distance between point A to B. So if we go for the Euclidean distance or say L1 distance, so let's say this is 0.5 plus 0.5. So Euclidean distance or L1 distance is 1. But Mahalanobis distance between A to B is found is 5. So that you need to compute given the what is called is covariance matrix. Okay. So you do it at home. You are still in at home. Okay. Now there are some properties of the distance. Okay. So that is one thing is distance between some of the. It is not necessary that all of the distance of similarity measure must satisfy this set of properties. Okay. So if these are the properties, some of the distance measure may satisfy. Okay. So therefore, here distance between 2 points is always greater than 0. If it is 0, then it will be the same point. And distance is symmetric. That is, distance from x to y is same as the distance from y to x. And then third point is the triangle inequality. So triangle inequality is, you know, the distance from x to y plus distance from y to z is always greater than equal to distance from x to z. Okay. If any distance measure satisfy these 3 properties, then this distance measure is called the metric. And Euclidean distance is a metric. Okay, for any Euclidean distance or any say Minkowski's distance, those are all the metrics. So let's say L1, L infinity, and everything is in Minkowski's distance is basically the metric. Okay. Similarly, what is called is similarity measure also will have the properties. That is, if x and y is the same, then it will be maximum, and it is symmetric also. Okay, but as I said, keys in many applications also, it's not necessary that it should be the distance should be the symmetric, or similarity measures may not be symmetric. One example, say, let's say you might be a friend of someone else, but say she or he may not consider you as a friend. You may consider him or her is a friend, but he or she may not consider you as the friend. So therefore, that relation may not be symmetric. Okay, so that is the example of symmetry. So now we'll go in more details like how to compute the similarity between two vectors. Okay, so there are some standard measures to compute similarity. So that we'll go through. So common situation is that object X and Y have only binary attributes. Okay. So in that case, what do you do it? Either value is 0 or 1. We need to compute the similarity. So one example is simple matching. So simple matching means in the both the cases, that is attributes is having the same value. Let's say F01 is the number of attributes where X was 0 and Y was 0. Y was 1. That means it is not matching. F10 is the number of attributes where X was 1 but Y was 0. So this is also not matching. For F00, the number of attributes where X and Y both are 0, 0. And the number of attributes where X and Y are both are 1. Okay. So in case of the simple matching, so it will consider how many times or how many attributes agrees. So let's say you have 3 attributes. And out of these 3 attributes, how many times the attributes agrees on the value 0 or 1? Means both the attributes says key it is 0 or it is 1. So that is for F11 and F00 divided by the all number of attributes. Okay, so that is the total number of attributes. Okay. So this is something called simple matching. Did you understand?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now there is a measure is called Jacquard. Okay. So Jacquard give important only whenever both are 1. As I gave example in earlier class, let's say you 2 of your friends went for shopping and they purchase some of the items, and obviously in the store there are many number of items. Both of them did not purchase, right? So now if you give the important, that is many zeros, and then occasionally there is no similarity, and then occasionally there is a similarity. So then what we will find ki both of them have very good similarity. But that is not the right thing, because what we do it, we are giving important, equal important if both the guys purchase the item, same item, or if they do not purchase same item. We are giving both important to both of the things. So therefore it is appearing that each object is similar to other objects. So therefore, this will not give the right analysis. So what is done is what we'll analyze that how many items both of them purchased, and then we'll consider those values F11. And while we'll out of this one, we won't consider that how many items they did not purchase. Instead of what we do it, we'll consider the how many items they purchase, both of them purchase, and how many items both of them purchase a same item. So therefore F11 is the indicate that how many item both of them purchased, and this is indicate the total number of item they purchased. Either maybe one guy purchased, other guy did not purchase. That also will be considered here, because in this example F01 it indicates that first guy did not purchase the item, however second guy purchased the item, and F10 is the reverse way around. That is first guy purchased but second guy did not purchase, but third one is actually the item both of them purchased. Okay, so that is giving something called the Jacquard coefficient. Jacquard is very familiar measures for especially in binary attribute. So it was introduced in long back, that is 1889 or 90 around. Okay. So yeah, we have a example here. We can check it. That will be very much easier to understand. That is, we have a, say, let's say X be an item and Y be another item, and then we have the attributes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 attributes or 10 dimension, 10 features. Okay. So now what do you do it? We compute the SMC. What is that? Wherever the zeros, that will be also counted. So 1, 2, 3, 4, 5. And wherever 1, there is no 1. So then still let's say X and Y, you cannot see that both of them have purchased same item. Nowhere. Still, if you compute the SMC, it will give 0.7, and 0.7 is similarity is quite high. Okay, so because there are 10 items and then you get 0.7, but maximum you can get 1, but you are getting 0.7. So that is means both of them are quite similar to each other. But that is not the right analysis, as I said, because there are many zeros which you are considering. But in case of the Jacquard, we'll see how many times they agree. Nowhere they agree the same item. So therefore this is 0. So therefore Jacquard value will be 0. Okay. So that is the difference for SMC. SMC is nowhere is used. Okay. But Jacquard is used in many places. Obviously not all, because then there won't be any improvement over similarity measures. Okay. So there are many similarity measures. Some of the similarity measures are quite popular in particular domain. Okay, so that we'll see later. Now is the cosine similarity measures. So cosine similarity is something if you have a two vector, and then it is basically the angle between the two vectors. So cosine cos theta, sorry, cosine of the angles between two vectors. Okay. So how do you compute it? So this is the dot product of the two vectors and then individual L2 norm. Okay, that is the length of the vector. So one example is the best. Okay, so many times we students, including faculty, learn through example. Okay, so why I am saying slowly? Because machine learn through example. Okay, so many times it becomes easier for us to learn through example. Okay, so that means sometimes we become machines in lighter note. Okay, so here D is the one vector, D2 is another vector. So what do we have to do? We have to compute the dot product. Okay, so dot product, if you see here, so all are 0. So we'll have the value 3 into 1 and 2 into 1. So you will have the dot product 5. And now what you do it, you compute the L2 norm for these values, this vector, that is D1, and it happens to be the value is 6.481. And similarly for D2 also will get 2.4. So there will be another bar here. So that symbol is like norm. Okay. And for vector, it is like L2. Okay. So therefore it is not mentioned. Otherwise we have to explicitly mention. For vector, it is like we represent the L2 norm. Otherwise, if you represent some other values, then we have to write explicitly those values. Okay. And then what we do, we will get the cos of D1, D2. The cosine value will get 0.315. Now, if you compute the what is called Jacquard, we'll get the different value. Okay. But in case of the comparing two documents, cosine is more popular than the other measures. Because cosine is basically it compute the angles between two vectors. Okay. It does not see the length. Okay. So it sees the angle between cosine of these two vectors, because these vectors are normalized. Okay. So if you normalize it, and then you will get the unit length, and then it is basically angle between two vectors. Okay. So therefore these two are, whenever you have a very large dimension. Okay. So it is found that cosine similarity is heavily used. So example is document comparison or news article comparison. Generally cosine similarity is used. Obviously nowadays we have the different mechanism to compute, that is the neural network. Using we represent into in different way, reduce the dimension, and then we obviously we go for the computing using cosine similarity. Okay. So there is on measures. So in heaven, that is something called extended Jacquard. Its formula goes like that: dot product, and then you take the norm square minus x dot y. Okay. Then another, maybe we can within next 4 to 5 minutes I'll conclude this class. So here we go. So earlier we computed the covariance matrix, right? There is a popular measure is called the correlation. Okay. And very fondly we say is like Pearson correlation. Okay, there are different measures for computing correlation. So one popular is something called Pearson correlation. This formula basically for Pearson correlation. Formula is not so complicated, but its slides looks a bit complicated. Let us try to understand what is this. So correlation between two vectors x and y. First, what we do it, we have to compute the covariance. Covariance is nothing but this formula. What is that? We have to compute the mean of the vector x. We have to compute the mean of the vector y. So now what, for each dimension, as you said, key x equal to 1 to n, as you know that n is nothing but the number of features. For each feature or each dimension or each attribute, what do we do it? We compute the value at that particular features, and then we subtract from the mean, and mean is subtracted from the value, and these orders should be maintained here also. And we do for the other attributes also, other objects of same attributes, that is the xk and yk is the value. Xk and yk are the values of the two objects on the same attribute. Say let's say k equal to 1. Please note it. What I say ki xk and yk are the values on the same attribute of the value x and another object y. And then you take the mean, as I said here, and then you multiply it. And you do for the all attributes, like in Euclidean distance, we also computed this square, right? Here, instead of square, we find the multiplications of the two values, that is basically subtracted from the mean of the values. So one way you can say this is a kind of normalization. Okay. So different values are different attributes have different values. We take mean from we take the differences and then we multiply. Okay. So then we'll do for the all attributes and then we'll take the mean. So that is something called the covariance. Okay. Now what do you do it on the, no, we have to normalize the whatever the value we got it. So this is not the true normalize here. So here is we divided by the standard deviation. Standard deviation is something like that. We know you take the square up from the mean and then you take the square root. So that is standard deviation for x and standard deviation for y. Okay. So that will get the covariance value. So x is defined as mean, y is nothing but the mean. So this Pearson correlation is heavily used in case of the recommender system. Okay, in recommender system, very oftenly we compute the similarity between two objects using Pearson correlation. Even similarity between two customers using Pearson correlation. So in summary, in Pearson correlation, we have to compute the covariance. Covariance is nothing but this part. And then we'll compute the individual this value. So this value is nothing but this part. And this value is nothing but this part. So you take only the summation of this part and take the square root, only the summation of this part and take the square root, and you multiply it and divide it. But here, whenever we do it on the numerator, we have to multiply this value along with this value. Okay. I think in next, once I reach campus, I will use the tab, so it will be much easier to explain. Okay. So this is one example that how the correlation is computed. So there are two dimensional, as you can see, one is horizontal, another is vertical. So very often we say this is x-axis and another is y-axis. Okay. So correlation is one for this example. X is increasing, y is also increasing. Okay. So that is the correlation is one. Okay. And then where is -1? Can you see here? Here. -1. So x is increasing and y is decreasing. Okay. So that is something called one value is increasing here, another value is decreasing here. So that is the example of, say, this is the value here. Now, what is the y value? Y value is decreasing, or let's say in other way around, what we can say is x is here, y is here, and then it is x is increasing. Okay, this part I will explain here in next. I think there is something. Okay, so what we see is value of x is also increasing, but value of y is also decreasing in. Okay, let me explain here. So as you can see, is value is increasing. Okay, x is increasing here, y is increasing here, and both x and y is increasing on the positive tone. So therefore, the what is called is correlation is positively correlated, and that value is maximum, that is 1. Okay. So this part I will explain, okay, in next class. So one example, this is a drawback of the correlation, is like we have a value x and we have a value y. So what is the mean? Mean is 0. Now you go back the formula here. What will happen? So if you put it here, then we'll see the correlation is 0. And this is nothing but the value for y equal to x square. If this is negative, y is always positive. So in that case, actually this correlation is not the right thing to represent. Why it is not right thing? Here if you see this part is increasing. So 1, 4, 2, 9, this is also increasing, this is also increasing. But whenever x is decreasing, but this is increasing. So therefore, for many applications also, Pearson correlation is not good thing to use. So therefore, everything depends on the application. So in the next class, I will explain this part once more. That is Pearson correlation. Okay. So I stop in at this point here. So as I said, tomorrow I have a project presentation to DST. So therefore, I'll postpone the class and morning 8 to 9. So instead of that, I will take class from 7:30 to 8:30 night. Okay. So do you have any confusion apart from the last slide? So if you have any confusion, please let me know. No confusion.
No, sir.
No, sir.
No, sir.
Really, you don't have any confusion.
Yes, sir. No confusion till now.
Okay, then I stop at this point. So hopefully many of you will join tomorrow at 7:30. And tomorrow is Friday, so we'll use the same schedule, that is 5-day schedule for meeting. Okay. So thank you all.
Thank you, sir.
Thank you, sir.
Thank you.